Hello everyone, welcome back to Pseudocoder. This is Ravina, and today we are going to solve lead code problem number 23, which is merge case sorted lists. This problem is popular with Amazon and Facebook, which is now known as Meta. If you like my videos, give it a thumbs up and comment on it. It really helps my channel, and subscribe to it if you want to get notified about the upcoming videos. Okay, so let's dive into our problem here. Our problem says that you are given an array of k linked lists. Each linked list is sorted in the ascending order. You have to merge all the linked lists into one sorted linked list and then return it. So let's see how what the actual let me explain what the problem means. Let me go to my notepad. Okay. So it means that there's a list of linked lists available to us. So this is one linked list, second and third. And these linked lists are actually sorted in the ascending order. Each list is sorted in the ascending order. What we need to do is we need to create one single linked list. Right now, it's a list of lists. So what we need is we need one single list that will have everything in the ascending order. So 1, 1, since we have two ones here, and then 1, 2, 3, 4, 5, and then 6. So we want one linked list in this fashion where all the nodes will be in the ascending order. So let's see how we can solve this problem. Um, I am going to solve this problem today using heaps. If you don't know what heaps are basically a tree, a very special tree-based structure where you can have, there are actually two types of heaps, minimum heap and maximum heap. It's actually a complete binary tree. So it's basically a tree-like structure, um, but a minimum heap will always have the minimum value in the entire tree as it at its root, whereas a maximum heap will have the maximum value here. So if I'm talking about minimum heap, it means that the top root of for this list would be 1. For this would also be 1, and for this will be 2. So these are heaps. If you want to learn in detail about them, I'm going to make a video about it, and I will leave the link in the description below so you can watch that instead. Okay, let's see how we can solve this problem. We are going to need a linked list. Let's call it result, and I'm going to initialize it with -1. Every time I'm going to go through this list one by one and then save this list as part of my heap. And I'm using minimum heap here. So let me do that. Okay. I have a for loop which starts from the first element. I go to the first element, I get 1, 4, 5. I'm gonna add it to my heap. I'm gonna add the first element, which is 1, my index, which is 0, and my element itself. So 1, 4, and 5. So these are the things I'm going to add to my heap. Okay, I go to the next element, 1, 3, 4. Since it's a minimum heap, it will create entry on the left hand side. So we have the first element's value, the index, and then the element itself. So this is my heap. This is how my heap is looking. Going to the next element, 2, 6. Again, add 2, which is the elements, the first value, which is 2. The index, which is 2 again, and then in the linked list. So this is how my heap is looking right now. The first for loop will be go through all the list inside the lists, go through the list inside the list, sorry, and add it to my heap. The next thing that we have to do is we have to constantly look into heap while it's not empty, and we are gonna pop out the elements from the heap. We are gonna add that element to our result linked list. How it's going to work is I pop out this, I pop this out, I get 10145. I'm going to create a new node with value 1. So I create a new node with value 1, and then I make my results next as that new node. Okay. Once I do that, if my node has a next value, so my node does have a next value, which is 4 and 4. So I'm going to add that to my heap again. So I'm going to add the element's value, which is 4. Since I added this to my to my linked list already, this is going to get removed. Its index is basically the same thing, which is 0, and then my linked list. So I have this now. I'm going to add this to my heap. When I add this to my heap sees that, oh, this is 4, but I have another value which is 1. So it's going to rearrange itself. It's going to make this element as its first. So let me update that. It's going to do 1, 1, 1, 3, 4. This is going to be my first element. On the left, it's going to be this. So let me update it with 2, 2, and 2, 6. And then the element that I pushed into my heap will come here. So it will become 4, 0, 4, and 5. Did you see what happened? As I took out that first element and then I processed it, I pushed it back to the heap, it rearranged itself, and now we have the second minimum character here with us at the root, which is 1. So we are going to repeat this procedure again and again until our heap is empty. So I pop the element again from my heap. I get 1, 1, 1, 3, 4. With the first element, I create a node. I create a node of 1, and then I link my results next to that node. I check if that node has a next value. It does. Then I create a new element to be pushed into my heap, which is the header next as the first element, the index, and then the uh, linked list itself. So when I do that, I push that into my heap. When I push that into my heap again heapifies itself. So it rearranges elements. Why? Because it has a 2, which is less than 3. So it will take this element upwards. So let me do that. I have then 2, 2, 2, and 6. And then this element will go here. So this will be now 3, 1, 3, and 4. Okay, okay. Once I have that, again, pop the element. So I popped it. I got 2, 2, 2, and 6. I create a node with the first element. I create node 2. I add my results next as the newly created element. And then I check if my element's next value is not null. No, it's not. So I'm going to create another element, which is the value 6, the index that gives carry on, and then the linked list itself. So I'm going to push this into my heap now. As you might have guessed, it's going to rearrange itself because I have 3 here. This is 6. This is obviously going to go to the right of the tree. Okay, so this is 3. This 3 must go to the top. Let me do that. So it's going to be 3, 1, 3, and 4. This little thing here is going to come to the left. Just think of it as a complete binary tree. Okay, and then on the right, the element that we pushed is gonna get created. So 6, 2, and then 6. Okay. What happens next? Again, pop. pop from the minimum heap, I get 3, 1, 3, and 4. I create a new node, 3, point my results next to that newly created node. I check if my node's next value is not null. It's not. So I'm going to create a new element with the element number, which is 4, the index, and then the linked list. When I push this in, so now if you see, when I push this in, it's going to see, oh, we have 2 4s here. What do? There's a tie. That is the reason we push the index, so that, even if there's a tie, the code shouldn't break. It should take the next thing for comparison. The next thing we have is the index. Here the index is 0, here the index is 1, so this becomes the minimum. This goes to the top. This becomes 4, 0, 4, and 5. When we insert this into our heap, it gets to the left hand side. So 4, 1, and then 4. Okay. Again, pop from the heap. I get 4, 0, 4, and 5. When I get that, I create a node, new node 4. I replace next results next with the newly created element. I check if my 4 has a next element. Yes, it does. So I create another element with 5, 0, and then my linked list. Push this into the heap. Since we have 4 here, which is less than 5, it's going to push that to the top. It's going to be 4, 1, and then 4. And 5 is going to get replaced here. 5 is 5, 0, and then 5. Okay. Well, we have to do it 3 more times. We pop out the element, we get 4, 1, and then 4 as a linked list. We create a node with 4. Results next will be this new node. I check if my current.next is null. It is null, so I'm just going to drop it. I'm not going to push anything into my heap now. When I don't do that, what my heap does is, since I popped this out, it's going to rearrange itself. This 505 will now become the node. So I have a node of 505, and this is going to be the child. Oops, used the wrong. Okay, this is going to be the child. Okay, now I am going to pop again. Pop again from the heap. I get 5, 0, and 5 in the linked list. I create a new element in the linked list with 5. Point results next to that element. And check if my nodes next is not is null. Yes, it's null. I'm just going to drop it. No pushing to the heap. Once I do that, then this is gone. We just have one element in our heap, and that is our root element. So this is our root element right now. I'm going to pop this out. So pop this out. I get 6, 2, and then 6. I create a new node with 6. The results next is that new node. So do you notice we got our single linked list in the ascending order, and we are just going to return we are going to preserve the head, and then we are going to return it in the end. And when we return this is our solution. Okay, I hope this was clear and is helpful. Let's go on and write some code. It's going to resemble it the exact same way, so you don't have to worry about it. Okay, let's start. Let's start by, we are using a heap, so I'm going to import it first. So I do import heap queue. Okay. The first thing for heap queue, I actually need a heap list. So I do that. My head will be a list node of -1. That's what we did here. If you remember, the first node the first node, we create it with -1. So I did that. And then I'm going to preserve my head into my root. So I'm going to do root is equal to head. The first thing that we want to do is go through the list of lists and then add it to the heap. For that, I'm going to, for index and the element in enumerate lists, I am going to check if my element is not empty. If my element is not empty, then only I want to push it to my heap. So I do heap push. I push it to my heap element. And what I'm going to do, this is the tuple. The first thing was the element dot value, which is the first element in the linked list. My index, that is used for when there is a tie between the value, the code shouldn't break, it should use the next element, which is the index. That's why we have it. And then the element itself. That's all. That's how we load up our heap. Once we do that, our heap is going to have that structure that we saw earlier, where each list is going to be in a tree-like structure where the one with the minimum value is going to be at the top. The next thing is going through the heap, popping it out, and then creating the node. And then if there is anything to the next of the node, then just push it. So while the heap is not empty, I'm going to pop out my heap's first element. So it will be heap q dot heap pop, and I'm going to pop from that heap. This is the syntax that we use in Python for heaps. Don't get confused. It will be something similar in Java, C# or any other language that you're using. Just make sure that you have to insert three things: the element dot value, the index, and the element itself. And while popping out, you can have three things that you're expecting. The second thing I'm going to do is I'm going to create a node with the newly available information that I have. So I'm going to create a list node with the value that we stored. Okay. And then I'm going to just advance my head, and head is equal to head dot next. The last thing here, what we have to do is we have to check if our node's next, if we have a next element in the node. So we got the element. So this is we got the element. We want to check if there is a next node. If so, then we want to push to a heap. So that's what we are going to do. Node dot next. It's going to be heap q dot heap push. Push it to the heap with my node dot my node's next value. So that's how you write it. Node dot next dot value. It's the next node's value. The index, and then finally the next node value. In the end, just return my root dot next. Since my current element of root is a list node of -1, I want to return its next value. Okay, let's try. Let's see if we can run this code. Okay, it runs. Let me submit it. Yeah, submitted faster than 93.46% of Python submissions. I think that this is, a really easy way of doing this problem, and also very logical, intuitive. If you know how heaps work, there are very similar problems like this in LeetCode, and you can approach these problems. So let's now talk about the space and time complexity of this problem. The time complexity of a heap is actually n log k, where where n is the number of nodes that we have, the number of nodes in a list, and then k would be the length of the number of nodes that we have inside the heap. So right now our heap was always three, size of three, because we had just three lists, and that is our k. Whereas n is all the elements that are there in the list of lists. So our time complexity here is n log k. Talking about the space complexity, all the things that we really needed here is first the heap and then the result. So if you think about it, the heap and results, everything, it's actually at the maximum it's gonna hold O of n elements. Even our result, even our result, if you look at it, it's holding O of n. It's holding all the elements, and it is thereby O of n. And the space complexity is O of n. Okay, I'm gonna upload this code to my GitHub channel as usual. You can find the link in the description, and you can also find a link to Discord. So please, join my Discord channel. We can connect, and if you have any suggestions for the videos that I should be making, please comment that down, and like the video. It really helps. And we have the same. I have been making Hindi videos lately. So I'll have the same video in Hindi coming up later in the week. So stay tuned and happy coding.